Okay, everyone, today we are going to go through the entropy balance for open systems. Remember, entropy balance is just a tool for accounting. We use it just to keep track of where entropy goes, where it came from, and how it moves. So we've done that previously for closed systems. Now we're going to adapt it to open systems when we have mass transfer. So what I'd like to do to start is just kind of draw an analogy with energy. Okay. Remember that when we talked about energy and we did energy balances and energy accounting, for closed systems, we dealt with before and after. So initially, some substance was in some state, and then we did some thermodynamic things, and then afterward, it was in a different state. Okay, so we dealt with before and after, and we also dealt with quantities. Okay, so we had a quantity of heat transfer, we had a quantity of work, we had a quantity of internal energy change. And then when we moved to start talking about open systems, instead of before and after, we had inlets and exits. So substances entered an open system in one state and exited in a different state. And instead of dealing with quantities, we dealt with rates. So instead of an amount of mass, we had a mass flow rate. Instead of an amount of heat transfer, we had a rate of heat transfer. Instead of an amount of work, we had a rate of work. So when we move to entropy and we do entropy accounting, we're going to have the same sorts of changes when we deal with open systems. Instead of looking at before and after, we're going to look at inlets and exits. And instead of looking at quantities of entropy change and quantity of entropy movement, we're going to look at rates. So as we talk about entropy, let's remember what the closed system entropy balance said. So the closed system entropy balance said that the change of entropy inside a box was equal to the integral of heat transfer over temperature plus the amount of entropy generation. Okay? And as we go to an open system, this equation is going to change in just the way that the energy balance changed. So remember, in the case of the energy balance, change in energy was equal to energy in and out by heat transfer. And then when we moved to an open system, that change in energy became a rate of energy accumulation, and that was equal to a rate that energy came in and out by heat transfer minus a rate at which energy came in and out by work plus a sum over the inlets of energy coming in with mass flow at the inlets minus the same thing over the exits. Okay, so as we went from a closed system to an open system, the amount of energy change became a rate of energy change inside the box. The amount of heat transfer became a rate. The amount of work became a rate. And then we had to add in terms for mass transfer. When we do it for entropy balances, we're going to do the same thing. So if I have some arbitrary open system and there's mass flowing in and out of that open system, I draw a box to define my system. Instead of dealing with the amount of entropy change in the box, we're going to deal with the rate at which entropy accumulates inside the box. And the rate of entropy accumulation has to be the difference between the rate at which entropy comes in and out by the three ways that entropy can come in and out. One way that entropy can come in and out of a system is by heat transfer. Heat causes entropy changes. So heat transfer is one way that entropy can come in and out. What we're going to do with this heat transfer term is we're going to get rid of this integral and we're going to say, all right, instead of integrating over a temperature change, since the substance is changing temperature as it goes from the inlet to the exit, we're going to assume that heat transfer could be coming in at multiple points when the substance is different temperatures. So we're going to break that integral into a summation, and we're going to sum, instead of doing an integral of dq over t, we're going to sum every heat transfer divided by the temperature at which that heat transfer occurs. But since we're looking at rates, we're going to change it to a rate. Okay? So as we start doing entropy accounting and looking at what the rate of entropy change is inside the box, the first way that we can change the entropy inside the box is through heat transfer. And we're going to break that integral up into pieces everywhere that heat transfer is occurring. So maybe this is Q1 and Q2 and Q3 and Q4, and we just need to know the temperature of the substance where that heat transfer occurs. In practice, that summation is usually just going to be one term or it's going to be zero. But For the sake of completeness, we leave open the possibility that maybe you have a long pipe and maybe heat transfer is occurring at different temperatures along the pipe. So there's the first term. We've switched the amount of entropy change by heat transfer to a rate at which entropy is moving into the box by heat transfer. For entropy generation, we're going to do the same thing. We're just going to take that sigma and put a dot on it. Instead of looking at the amount of entropy generation, we're going to look at the rate at which entropy gets generated inside the box as irreversibilities continuously occur. So mass is continuously flowing through, whatever friction and other sources of irreversibility are present, those are constantly acting on the mass that moves through, so they are constantly occurring. There's a rate at which that entropy is being generated. And lastly, we have to add in terms for mass transfer. Now this should be fairly straightforward and fairly obvious because mass has entropy. We've talked about how to look up the entropy of a substance. So if mass moves into my box, it's bringing its entropy along for the ride. And just like mass brought energy along for the ride, it's bringing entropy. So everywhere there's an inlet, I'm going to have to sum over the inlets. Everywhere there's an inlet, there's mass flowing in, and that mass flowing in is bringing entropy along for the ride. And everywhere there's an exit, mass is leaving. And everywhere that mass is leaving, it's bringing entropy along for the ride. And that's it. There is our open system entropy balance. So now that we've derived this equation, the open system entropy balance, let's start breaking it down and looking at a few notes about how it gets modified under certain circumstances. The first thing that I want to note is that there's no W in that equation. There's no work in that equation. Entropy does not move with work. Doing work on something does not change its entropy. Taking work out of something does not change its entropy. There is no work term in the entropy equation. Work does not affect the entropy of a substance. Second thing that I want to note is if you see the word reversible. So if you have a thermodynamic process or a system that's reversible, what that's telling you is that there's no irreversibilities. If there's no irreversibilities, then there's no entropy generation. And what that means is that sigma dot is equal to 0. Third note, what if it's steady state? Well, just like with energy, if it's steady state, then nothing can be changing with time, which means that you cannot be accumulating entropy inside your box, because if you were accumulating entropy, then the entropy at one point in time would be different than the entropy at another point in time. So steady state means that the accumulation of entropy, the difference between what's going in and what's going out, has to be 0. Okay, this is the same thing as saying that if you spend what you make, then your bank account doesn't change, right? If what's going in equals what's going out, then things don't change. So if nothing's allowed to change, then what goes in has to come out, which means that S dot CV has to be 0 because that's the accumulation term. That's the difference between the entropy coming in and the entropy going out. Going further, what if we have one inlet and one exit? Well, then our summations only have single terms. Another one. What if it's adiabatic or insulated? Remember, those terms mean the same thing. If it's adiabatic or insulated, either way, that means that heat transfer is 0, which means that that sum of Q dot over T is also equal to 0. And finally, let's look at sort of the most common scenario for thermodynamics, which is that you have a steady state process, so something is flowing steadily through the system, and you have one inlet and you have one exit. So for example, it could be a turbine or a heat exchanger or a compressor or any number of a variety of different open systems that we've talked about previously. If they're operating in steady state, let's look at how that equation reduces down. First, remember that in steady state, the accumulation of mass has to equal 0, and that's equal to the sum over everywhere mass is coming in minus the sum over everywhere mass is going out. Right? That's our mass balance. And if we have one inlet and one exit and we're in steady state, then that means that mass in is mass out, which we'll just call m dot. Moving on, if we go to the entropy balance equation, S dot CV is sum of Q dot over T plus sum over the inlets of mass flow rate times entropy at that inlet minus the sum over the exits of the mass flow rate at each exit times its entropy plus the rate at which entropy is generated. Now, if we're in steady state, S dot CV has to be 0. And if we have one inlet and one exit, we have one term in each of the summations, and we only have one mass flow rate. So this equation becomes 0 equals the sum of Q dot over T plus M dot times S1 minus S2 plus sigma dot. Okay. And just like for the closed system entropy balance, there's only a few options for each of these terms. This Q dot over T term, option 1 is that it's equal to 0. And your keywords there are is that if I tell you that it's adiabatic or insulated, then that means that that term is equal to 0. Another option here is that you have a constant or average temperature. If you have a constant or average temperature, then that summation turns into a single term, and that's all you need to do. And those are the most common scenarios for that Q dot over T term. This S1 minus S2 term, these are properties. Okay, so these are the things that you get from tables, or in the case of an ideal gas, you get from the entropy equation for ideal gases that we've talked about previously. But however you get properties for your substance, that's where they go, is right here in this term in the middle. The sigma dot term, like the Q dot term, also only has two options. Option 1 is that it equals 0, and the key word there is that if I tell you it's reversible. Because reversible means no irreversibilities. No irreversibilities means no entropy generation, so that term would have to be 0. Option 2 is that it's what you're solving for. There is no other way to sort of calculate what sigma is other than by this equation right here. All right, so I hope you followed all of that. What we're going to do now is just a quick example to show you how this gets used. So we're going to do problem 682. Okay, so here we have problem 682 written out. All right, so let's kind of walk through this problem and see what we can do. So first of all, it says propane. So our substance is propane. It's important to remember that propane is something that we get properties out of a table. We don't use the ideal gas law. We don't use the ideal gas entropy relation. We get properties out of tables. So propane at 0.1 megapascals, 20 degrees C, enters an insulated compressor. Okay, so our system is a compressor. So let's draw a compressor. So compressors have one inlet and one exit. They also have a work input. So let's draw that work input so that we remember that that's there. Okay, and it's an insulated compressor. So let's draw in some insulation as a reminder. And we can write down our properties and process information. So if propane at 0.1 megapascals and 20 degrees C enters an insulated compressor, that means that P1 is 0.1 megapascal and T1 is 20 degrees C. And it says that the insulated compressor is operating at steady state, so let's write down that this is a steady state compressor. And it exits at 0.4 megapascals and 90 degrees C. So if it exits at 0.4 and 90, then that means that P2 is 0.4 megapascals and T2 is 90 degrees C. And that should make sense because the pressure should go up in a compressor and the temperature should go up too because you're putting work into it, which should be raising the enthalpy. I also notice right now that at state 1 I have two properties, which means I can get all other properties. At state 2 I also have two properties, which means I can get all other properties. Okay, so I'm in pretty good shape. It also says that I should neglect kinetic and potential energy effects, so let's write down that Ke equals Pe equals 0. That'll be useful to remember. And now we're asked to determine a couple of things. So let's go to step 4 in our methodology, which is to remind ourselves that this is an open system. And since it's an open system, that means we're going to use the open system energy balance and the open system entropy balance as necessary. Okay, so let's take this problem part by part. And the first thing we're asked to find is the power required by the compressor. Well, we only really have one equation that has a work term in it, so let's use that one. That's the energy balance. Okay, so as we start part A, let's apply an energy balance. And as we hopefully all remember, the energy balance for open systems is given right here. Okay, so as we move through this energy balance equation, let's use our brains. So first of all, we know it's in steady state, so E dot CV is going to be 0. We know that heat transfer is going to be 0 because there's an insulated system. We know that there is work, but it's going to be a work in. So as I start rewriting this equation, 0 equals negative work out, which is plus work in, plus sum over the inlets is going to become one term because I only have one inlet and I have one exit, so I have one mass flow rate. And kinetic and potential are going to go away. Enthalpy is going to stay because it always stays. And what we're left with is H1 minus H2. Now, we're asked to solve for work, but we're asked for work in kilojoules per kilogram of propane flowing. So that's work per mass. So work in over mass flow rate is equal to H2 minus H1. Okay, we've got two properties at state 2, so we can get H2. We've got two properties at state 1, so we can get H1. And if you look up things in the tables and you do the math, this becomes 121.6 kilojoules per kilogram. Okay, so we finished part A. Let's move on to part B. Part B asks for the rate of entropy production within the compressor in kilojoules per Kelvin per kilogram of propane flowing. Well, we only have one equation that has an entropy production term within it, and that's the entropy balance. So let's use that, and then let's apply our brains. Okay, so entropy balance equation for an open system we just wrote above, and let me write it now here. Okay, now that it's written, we can go through it term by term. First term on the left, S dot CV, that's going to be 0 because we're in steady state, so there's no accumulation of entropy. Sum of Q dot over T, Q is 0, so that whole term is 0. Again, we have one inlet and one exit, so we have one mass flow rate, and what we're left with is 0 equals m dot times S1 minus S2 plus sigma dot. So we were asked to find the rate of entropy production per mass flowing, so we want sigma dot over m dot, which is equal to S2 minus S1. We have two properties at state 2, so we can get S2. We have two properties at state 1, so we can get S1. And so what we find is that sigma dot over m dot is equal to 0.117 kilojoules per kilogram Kelvin. And the fact that that's greater than 0 makes sense because it shouldn't be less than 0. A reversible system would have no entropy generation. Otherwise, entropy generation should always be positive. So that's it. We're done. We finished the problem. Having now finished that problem, let's kind of walk through what we just did and let's build a new methodology that utilizes this new entropy balance tool. So our thermodynamic process problem methodology. We're going to just build on top of what we've done previously. So step 1, as always, is identify our substance because that determines the rules by which we find properties. Step 2 is to draw a schematic because that helps us visualize what's going on and make sure that we don't forget important things. Step 3 is to write down our properties and process because that's all the sort of process information that we need to keep track of everything. What do we know and what are we given? Step 4, again, is to remind ourselves, is this an open system or a closed system? Because whether it's an open system or a closed system determines which energy balance we use and which entropy balance we use. This is where things are going to start to change just a tiny bit. Step 5 is still going to be an energy balance, followed by step 6, which is that EQW, use your brain step. You know, what kind of energy is relevant? Is there heat transfer? Is there work? If so, what kind? But that's going to follow up with step 7 and 8, which now is entropy balance, which is our new tool that we've added in. And that has to be followed again by using our brain. We'll call it the SQ sigma. Is there heat transfer? Is there entropy generation? Do we know that it's maybe isentropic? use all those pieces of information to figure out what we need to get. And then our last step, which we've had previously as well, is the mass balance. And remember that one's only needed if you have multiple inlets and exits. Now, one thing I want to mention here is that this energy balance and this entropy balance, those are all interchangeable depending on what you're looking for. Okay, so even though I've written it with energy balance first and then entropy balance after that, the real thing that you would need to do is just use whichever tool is appropriate for solving for the thing that you're solving for. So maybe that means you do the entropy balance first. Maybe it means you do the energy balance first. You do whichever one is going to get you what you need. And I guess I should probably put mass balance into this same interchangeable thing as well. You have three tools and you use them in whatever order you need to in order to solve the problem. But that's it. So that is our new methodology with our new tool put in place. So that's all for this lecture. We'll see you again when we'll pick up some more stuff about open systems and entropy balances.